Welcome to Ask and Learn.
In this problem, we have a car that's going around in a circular track. We want to find the speed of this car when it reaches at the bottom at point B, and we also want to find the normal force that's being produced at that point as well. So we're given the mass of this car, which is 250 kilograms, the radius of the circular track, 8 meters, the velocity at the top at point A, which we'll call VA, 3 meters per second, and the speed you want to find, call it VB. So the weight of the car is producing a work, and because we're dealing with velocity, we know that this car also has kinetic energy involved. So since we're dealing with work and energy, we can use the work energy principle, which is the initial kinetic energy plus the work being done by the forces will equal the final kinetic energy. We can expand this a little bit. So we have for the initial kinetic energy 1/2 m times VA squared plus, and now let's leave the work alone, is equal to 1/2 m VB squared. So we're looking for VB, the velocity at the bottom at point B. So now let's look at the work being done by the forces. Well, the only work involved is weight, and so we know work is the force times the distance. So we have the weight of the car times the distance it travels, S. We know what weight is. Weight is just mass times gravity times S. So let's plug this in. We have mass 250 times 9.8 times S. Now S is the total distance that this car travels. So we know that if we know that the radius is 8 meters, from point A to point B is actually the entire diameter of the circle. So we can say the distance traveled for S is 16, just double the radius. So let's plug this back in to our equation and plug in the numbers we know. So we have 1/2 times m 250 times 3 squared plus 250 times 9.8 times 16 will equal 1/2 times 250 times VB squared. So again, we're solving for VB. So let's clean this up a little bit. So on the left side we have 1,125 plus 39,200, and then 250 divided by 2 is 125, and we can divide that out to this side. So we have 125 will equal VB, and VB is squared, so we take the square root of both sides to get VB by itself. So we have the velocity at the bottom at point B, VB, is equal to 17.96 meters per second. So now let's find the normal force at this point. So first let's draw a free body diagram just to see the forces involved on the car. So we know at point B we have the weight pushing down mg and the force, the normal force, in the opposite direction. So since they're in opposite directions, when we use Newton's second law, we have Fn minus mg will equal mass times acceleration. And here, acceleration is centripetal acceleration since we're dealing with a circle, and that is equal to the velocity squared divided by the radius of curvature, which is 8 meters. So let's put mg to the other side. So we add mg to both sides. So we have Fn is equal to m v squared over rho plus mg. So now it's just a matter of plugging in the numbers. We have Fn is equal to m, which is 250, times the velocity squared, 17.96 squared, divided by the radius 8, plus 250 times 9.8. So we get for the normal force Fn is equal to 12,530 newtons.